So I took this doubling every year and extrapolated it 10 years from 1965 to 1975 from 60 components to 60,000 components on a chip.
First thing you have to tell him is,
Yeah.
guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
The future is parallel. Single cores are not getting any faster.
Right, so today we are going to start a new short topic, which is instruction set architectures, which defines the way how processor would that choose see the functionality of the processors. But before we start, it's always a good idea to remind ourselves where we are coming from. So last week we were talking about all computers look similar because they are also called von Neumann computers. And in von Neumann computers, we have processor, we have memory, we have storage. And when we compile a program, it's stored in a storage. And when you want to run it, somewhere in your system would load that program into the memory. And then the processor will fetch the instruction part of your program and see what the program really wants us to do, and if necessary, we will also access the data part as well. So that's how von Neumann architecture works. And the beauty of von Neumann architecture is that with these three components, by loading different programs, it's going to perform differently. And then we talk about the classic way of measuring performance is looking at by how much time the processor needs to execute the program, because if you look at the design of von Neumann architecture, it seems that so someone saying that the previous slide is not on the website yet. My suggestion is that you probably have to refresh the browser and don't use the Canvas one, because the Canvas embedded one only update once a day, but I did upload the preview slides early this morning. So the summary, well, so for the performance equation, conventionally it's just because processor is the conventionally the only unit that we could use to execute a program. So the performance is completely depend on that. So the execution time is depending on how many instructions you have, that's the instruction count, how many cycles per instruction, and how much time it takes for a cycle. So that's the execution time. And then in terms of a speed up, the only definition we have is if we want to say speed up of y over x, then it's the execution time of x over y. And here are the factors that you learn can affect each component in the execution time equation. And some of you really get confused a lot, which I saw from Piazza saying that, well, I saw the speed up is this. How can I calculate my speed up? Again, right? The only definition of speed up we have is this. So if you found that you have trouble of applying this format of speed up, which is a derived form from the basic speed up equation, then just use the base one, right? Try to get the execution time, don't be lazy, right? And for this one, it's something called M-DOS law, in a way that it's rescaling your baseline execution time into one, and then evaluate the speed up after you apply a certain optimization. So if the information you gather doesn't give you this f, the fraction of time that you can affect in a program, and you don't have the speed up, you cannot use MDOS law. And in fact, MDOS law has a lot of use cases, and for example, you can use in multiple optimizations as well. So some of you have done this in the lab and figure out how to do it, right? But one of the questions was asking about, oh, wow, how can I evaluate my overall speed up? And turns out well, figure this out, right? The whole program is composed of baseline underscore int, matrix column major, plus and everything else. So that's the baseline, right? And some of the in the lab, some of the part is trying to give you some hints about how can I evaluate the potential speed up of this using optimization, and the potential speed up of using this of optimizing this, right? So after getting that, apply this equation. This is how you get MDOS law speed up from MDOS law. However, again, right? This is only useful if you know the breakdown of the execution time. So for example, if you have no information regarding this, and also is useless, right? And if it turns out that your optimization is going to cause the slowdown of either functions, don't use this, right? And if your optimization is going to incur additional overhead, then don't use this, right? Otherwise, if you found that I cannot use this, again, this is the right form of speed up. This is not the original form, right? If you cannot figure out how to do it with this, just use the original form. It won't kill you, right? So, but one thing we love about MDOS is that the MDOS really gives us a lot of fruits in looking at some of the insights in performance optimization. So for example, if you assume the speed up is unlimited, you can see, well, what's the maximum speed up that I can get? And another thing is that for the multiple parts optimization, right, you could actually looking at, okay, if I have a limited resource, what's the most common case that I should invest my resource on? And third, right, exploring, you also use it to exploit multiple parallel optimization if the parallel optimization is not going to incur too much of the overhead. And finally, right, another thing is that single core performance still matters because, again, right, if you think I have a limited number of cores, and at the end, the 1 minus f part, which is the non-parallelizable part, is going to determine your performance, right? So here's our current standing of each team. And last week, I think all of you have done a great job in having those conversations and discussions. So today we are starting with this conversation. So not sure how many of you have experience with Tesla or something, but I am thinking about, well, some of you might be working for companies like Tesla in the future. So if you are having chances of designing a completely new car, and how are you going to expose the car feature to your drivers? All right, looks like everyone is back. So, is there any of you like to share your thoughts about, okay, so Hayat, you already have the idea. What
Yeah.
is, yeah.
So basically, when designing a car, one major concern is that the driver should not be distracted, right, from driving. So if everything is in
Mm-hmm,
one place, in one particular place, like Tesla has their
mm-hmm,
infotainment screen, which has every feature. You can adjust
mm-hmm.
the AC settings, you can adjust the radio settings, everything. So if everything is close by and in one place, then it's easier for the driver. For example, the brake light should not be in the trunk, right? You wouldn't be able to reach the trunk.
Mm-hmm.
So yeah, everything
Okay,
around.
so everything should be, okay, everything at the same place. So
Yeah.
how, okay, who else? Or too young to have a car, too young to think about a car? Not a good example. Okay, Kevin.
I was just looking at it. Sorry, can you hear me?
Yeah.
I was just looking at it as from the angle of like conformity, I guess, to the industry or
Mm-hmm,
like to the standards. Like people are
mm-hmm,
used to things being in specific places. People are used to where throttle, clutch, brakes, steering is. People are used to where
mm,
controls are like window rolling up and down, seat going,
mm-hmm.
back and positioning. So I think you have to design the interface in a way that other people are already used to, socially used to using. So it's not
Okay.
like hard to use.
Okay. Uh, Elliot, you raised your hand once, right? Do you have anything to share?
Uh, Actually, Kevin and I were in the same group, so I would be saying the same stuff.
Okay. Okay. Okay, right. So you guys have a pretty good uh discussion, I believe, right? So first of all, it has to be following the convention that people would like to have, right? So if this is the way how I used to drive a car, or in a computer science, right? If this is the way how I would like to use the computer, it should be designed in that way, right? And or another thing is that it if I have many functionalities, right? I want to have a single place to start, right? So that's the design philosophy that you want for designing the interface of how drivers to use the car. And today we are going to talk about instruction set architecture. It's actually the interface between programmer and the computer hardware. So you will figure out that your discussion, and that's why I have this question brought up, because you will surprisingly, well, maybe not that surprised, but you will feel that when you are designing the instruction set architecture, there are some flavors and some philosophy, some debate about what's the right interface. But before we start, let me start with this, right? So this is something from Da Vinci Code, and I'm not sure why am I putting this up. Probably because I read this, and you know, computer architects, some people, they are really humorous. So some of our pretty famous professor at University of Wisconsin, hopefully God will forgive him for doing this. This is the version of Genesis he wrote. So he said in the beginning of electronic computers were without form, and darkness covers all computing. And these people like Eckert, Mauchly, von Neumann, and others said, let us use electrons, and electrons were used, and they saw it was good, right? So that was the convention people were using, like in the past, right? Computers are very hardware oriented. So it's all about functions, it's all about the operations that the processor supports. And then they figure out it's probably too difficult for people to use. So they divided the hardware which was below the instruction set architecture from the software, which was above. And the command is that the software be sequential, and they saw it was good. Okay, so today we are going to talk about this part. Do you feel like you are going to another church service today? So today we are going to talk about this part, the instruction set, which is like the light in Genesis, right? It's basically without instruction set architecture, there won't be anything like software industry. So it's really important, right? So being a programmer, how can you not know something about the instruction set architecture? So what instruction really is? What is an instruction set architecture? And then I will start with an overview of x86 instruction set architecture, give you an idea about x86 instruction set architecture, how that express and program, and talking about other instruction set architectures. So before we start, it's always a good thing to define what is instruction set architecture. So the instruction set architecture is actually the abstraction, or say the interface, or say the interface between you and the machine hardware. So you know that I am an intensive gamer on Pokemon, so I love these two ones, but they have completely different functionality, right? So being a user or a trainer, you must know all the features of them. And unfortunately, the Nintendo Switch provide a very good interface by abstracting their features into 4 different buttons. So by using different combinations of them, or just by pressing one of them, or press them in different ways, you just need to memorize that if I do like A, that's a small attack. If B, you have to press it longer, and it's a attack that's more effective. Something like that, right? So in this way, you don't have to memorize everything, right? And no matter what computer, well, no matter what Pokemon you are using, you all know that by pressing A, B, X, Y, it must work out in some sense, right? So that's the good thing about abstraction. So an instruction set architecture is like this: is an instruction set. It's a set of abstraction that defines what type of operations that we need to support, what type, how, and what's the format of this operations, and how many resources that we can use, right? Because by operations, it defines the processor part. And don't forget, for a von Neumann computer, we also have the memory. So instruction set architecture serves as the interface between hardware and software. It must contain this part. So now the question is that how many operations do we need to support, or what type of operations that we need to support? Then it completely flows back to the question, what are we going to use this computer for, right? So as many of you know, we are going to use this computer to run programs. And what are we going to do with the program, right? So if you think about this is the program that we are going to run. For example, a for loop, right? So to get this for loop up and running, right, a few things you have to do. First of all, you need to have control flow operations so that I can enter this for loop, and then I can see, well, if I want to stay in a loop of going out. And to judge if I want to stay in a loop or going out, we need logic operations to do things like comparison, right? And then if you want to calculate some of the mathematical result, or you just want to control the loop iteration, you all need arithmetic operations to control the loop index, right? And finally, again, our data is residing in the memory in the very beginning. So if you want to access data from user, you need memory access instructions, right? So basically, you can imagine, given this is von Neumann computer, this is how your program looks like, right? This instruction cannot be missed anyway, right? So a processor must support all of this, right? So in fact, what an instruction looks, or what a processor looks like, is a set of functional units that supports logical operations, simple arithmetic operations, complex arithmetic operations, branch for control flow, or memory operations. And for the user, like some of you just said, we hope to just have one interface, one place to submit them all, right? And that aggregation is indeed your instruction set architecture. So by talking with the instruction set architecture abstraction, or using the instruction set architecture abstraction, you don't have to talk with each functional unit explicitly. In fact, the instruction set architecture acting as the front end of your processor would distribute this workload to the right place accordingly. And all your program needs to know is, how can I translate my user program into instructions? And the instruction set architecture, the processor support this particular instruction set architecture. We would just handle that for you, right? And if you don't believe me that the microprocessor is just a collection of functional units, this is the functional diagram, the block diagram of a Skylake architecture processor. And as what Intel draws here, right? As you can see, well, they do have the memory unit, they do have this like branch unit, right? To decide the control flow, and they do have the LU. They have like LEA, which is used for address calculation. They have FMA, which is fuse, match, multiply, and addition as a separate unit. They have shift logic. They have divisor. They have shuffle units. Those all sorts of things like that, right? So the processor is indeed a collection of functional units. And with instruction set architecture, we don't have to have our program talk to individual functional units. It's all within the same umbrella called the ISA. So ISA is actually the contract between the hardware and software. It's an abstraction of the underlying processors, defines the set of operations that a computer can execute, defines the memory space that a program can use, and program a combination of these instructions. And there are many ways that you can implement these instructions. For example, you can use hardware support, and for newer architectures like Apple's M1, right? They actually use emulator to support x86 instructions for the legacy program, right? And well, fortunately, you are not in 141 and 141L. Otherwise, we will definitely ask you to use pen and paper to emulate the effect of the instruction set architecture. So that's also another way of implementing an instruction set architecture, by giving you guys a set of instructions and ask you for the feedback, right? So that's many different ways of implementing the instruction set architecture. So let's start with the one that's the most notorious, but also one of the most widely used, and one of the very historical one, that's the x86 instruction set architecture. So I would say x86, although people are complaining about its design, but it's actually a very natural design, right? And think about what we just mentioned, right? The x86, the processor is just a collection of functional units, right? So it's very natural that if I have logical operations or whatever operations that I need, I have an instruction to support it, right? So that's x86, right? So one of the examples is that, let's go back to this one, right? So this is the simple loop that we just seen, right? And in x86, what are we going to deal with it, right? So first of all, right, we want to initialize I equal to 0. So we must have some instructions like XOR, or even simple load store instruction that initialize the EAX to 0, right? And then want to compare if I is smaller than 100, so we start to have CMP out, right? And I want to do the increment of loop index, so I have the add instruction. And I want to do sum plus equal to AI, right? And some of you say, well, we want to design the instruction, we want to design the interface to fulfill what programmer used to, right? So if programmer used to have sum plus equal to AI, this kind of semantics, it's very natural to have an instruction like this, which is basically saying that EDX equal to EDX plus this memory location, right? And if you look at this memory location, this AI, the I is actually here, right? And this 4 is just telling you that, well, if this is integer, then this is 4, and ECX is the address of A, right? So everything is very natural, right? So this is x86. Now you might ask me the question, okay, now I want to jump back to the beginning of the loop. Okay, definitely we will give you a J and E instruction for you to jump back, right? So turns out, right, if I want to implement this simple loop, right, you will see this is how x86 does it, right? So essentially every statement has one instruction mapped to it, right? Every statement has one instruction mapped to it, right? So in this way, what's wrong with x86? x86 is actually pretty natural, right? As many of you said, it has to be aligned with the social behavior of the driver. And the driver here is actually the programmer, right? So if programmer love to write this kind of semantics, why not using this instruction directly, right? The translation is very trivial, very straightforward, right? So that's x86, right? And if you are interested to see how your C code can be translated to assembly, again, -S is the flag to use. And you should have experienced that a lot during lab 2. And if you haven't, it's a good enough sign telling me that you haven't started yet. So now, a quick question that I want you to discuss with your friends is that given these pieces of code, how many times, well, how many instructions will the processor is queued? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's go ahead to have a group discussion with your friends. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, we have two of you raise your hands, and actually, Hayat, you are a little bit earlier, so why don't you start?
Yeah, sure. I think it's so my group thought, all of us thought collectively that it's 401, because option D, because the first instruction would be executed once, and after the next four instructions would be executed 100 times each, because it jumps back to the tag L2.
Okay, so Elliot, do you agree with that?
Yep, that's what we got also.
Oh,
Yeah.
okay. So, and actually, it's pretty consistent with most of the discussion results, saying that we are happy with D as our answers. And as many of you said, right, it's indeed the case where, oops. So this is going to run for 100 times, right? And so we have four instructions here, so it's actually 400 plus 1. So the answer would be D. And some of you might get confused, right? So how many instructions in a program, right? How many instructions is queued by the processor? It's actually asking different questions. So if we are asking you about how many instructions in a program, in a compiled program, that's actually asking about static instructions, right? So then some of you already put the answer in the chat, right? So if we are asking for static instructions, the answer will be A, right? However, that's not what we are asking for, because the question is asking about how many instructions the processor will execute in total. So turns out that will be the dynamic instructions, right? So that is basically asking about how many instruction instances are going to be launched when you are running a program. So this part will be go through by 100 times, right? So sorry, 100 times, and there are four instructions here. It turns out that it's going to be D, 401, right? So now the question would be, if I am doing, okay, so maybe we can have a quick vote again. Let me reuse one of the question that we have in the past. So so now listen, if I am evaluating the CPU classic performance equation, A, B, C, D, what's the instruction count that I should be used? 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looks like this is also something that we have to discuss. Well, so that's why a lot of you were saying about we need more examples, right? So this is surprisingly the answer I got. So can some of you share your thoughts with us? So maybe that's a very big misconception that we have to brought up. So now, if for this pieces of a code, if I want to do the execution time equal to IC times CPI times CT, right? Which number should I be used for the IC? Can some of you raise your hand, share your thoughts with us? Okay, Hayat?
I still put D again, because
Why?
because we need the execution time for, it's called execution time, not compilation time, right? So
right. Well, it's the execution time, right? The
yeah, so the
execution
number
time,
of instructions
which
executed would be 401. So we would
it
probably
will be hope for one, right? So here
yeah.
here is the big concept thing. We have to be really, really clear, right? If I am asking how many instruction, well, if I'm asking about the performance equation, I am asking how much time it takes to execute a program. So it's the program in execution, right? So then that's the dynamic instructions, which is 401, right? Not other things, right? So not this, right? And I don't know what is this. I don't know what is this, right? But 401, that's the thing, right? That's the instruction count that you should be using, right? For the performance equation. So that's really, really important concept, right? However, if I'm asking you how big the compiled program is, like how many instructions are there in the compiled instruction, like how many memory space that the compiled code is occupying, then the static instructions is what you should be looking for. Hopefully that will give you a good idea about the taxonomy of these two types of instruction count. But in terms of performance evaluation, we are looking for D. Okay, so this is S86 instruction. Well, so here is the so some of you were asked, for this case, the static would be 5, right? That is correct. The static instruction, the compiled instruction, that is 5. Okay, so S86 instruction, as we said, it's very natural, but it's so natural in a way that there are many ways of using an instructions. So it's like, so somehow I would feel it's like the natural language, right? There are so many ways to describe one thing, or there are so many ways to use a word differently, right? So you must, like recently well, you know, since I migrated to United States, I start to figure out that the English is completely different from what I have learned from the textbook, in a way that there are so many slangs that the formal dictionary won't give you, but you can only find their true meaning from Urban Dictionary, right? So that gives you a good example about how complex the language system is. And S86 is pretty much like that. So for example, move instruction is the instruction of moving data between different locations. And turns out that the move instruction itself has this 8 different syntaxes. So the first syntax, in the first syntax, it's basically saying that you can move a constant value into a register. So all you need, so it needs an arithmetic operation that basically just perform like 0 plus 6 and put the value into the destination register. And you can also move a label, which is also a constant value, into a register And or you can move register values to register values. Or like this one, you are accessing the memory location with address, with the base address value stored in a register RBP -4, and then assign the value to the destination register. So your arithmetic operation is actually 2, because you have to -4 and then perform this assignment in a way that add 0 to the loaded value and store it to the destination. And there's one memory operations as well. And the move operation can also be written in a way which is a little bit similar to the example, the loop example that I just mentioned to you, that, well, the ECX is the base index. Oh, I think this is wrong. The ECX is the base index, base address, and this is the index in your loop array, in your array, and this is the stride of a loop, the size of a loop element. An array element. So this gives you the memory address. This part is simply the memory address part, right? And loaded to the EAX. So the whole thing actually has like 3 memory up, arithmetic up with 1 memory up. And this guy is even more complex, right? You can also have an offset. So it turns out that you have 4 arithmetic operations to just calculate the effective address. And then you can also put the destination and the memory address the other way around. Or you can also move a constant value to a memory location, right? So simply the move instruction has so many ways to use it. Hayat, do you have questions? Okay.
No, sorry, I just forgot.
Okay,
to
no
put
problem.
my-
No problem. Just make sure, right? So the move instruction has so many different ways in x86, right? And the arithmetic operations is also has a fruitful of formats. For example, like the sub L, you can use immediate values, constant values. You can also sub value from register to register, or you can sub a register value with the memory location value, the value in the memory location, or you can subtract a more complex memory indexing mode, or even more complex, or you can also subtract the memory location value from a register. So there are so many different ways that you can use the subtraction, right? So some of you were asking about for the third instruction in the previous slide, why not REBX equal to okay, so this is just because I written it incorrectly, right? So it's actually the other way around. Okay, so thanks for the correction. Okay, so as you can see, right, the arithmetic operations or the move operations, they all have many complex modes. And this is the branch instructions as well, right? So for branch instruction, it's actually have a 2-step. So it has to compare values and put them in a flag. And then the instruction is going to check the flag and to decide what direction to jump. Or there is also a unconditional jump, no matter what the condition is, we just jump, right? So there are also many types of branch instructions. So looking at these instructions, right, you will feel that, it's very natural, but it's so complex, right? And if you want to, be thinking about how we design it, and in fact, right, the x86 has way more instructions than we can handle. So x86, this is what I Googled this morning, right? It has 981 unique instructions and a total of 3684 instruction variants. So that's very complex. If you cannot imagine how complex is it, let me give you an example, right? So not sure how many of you is able to read this Wikipedia, but it basically tells you that Chinese language, which is a very complex language to learn, has at least 35,000 frequently used words, depending on which country you were looking at, which version of the Chinese you were looking at. That's not too far away from the number of instructions that we support in x86, right? So you could imagine the x86 is now as complex as a human language like Chinese, right? So that's very complex. However, if you really want, right, instruction like this single instruction could be rewritten as the instruction like this, right? So like this sub L -4 EBX EDX for EAX, right, is essentially saying that EAX is equal to the memory location equal to EAX minus the memory the content in the memory location here, right? So if you really want to avoid this very complex syntax, you can basically saying that, well, let me first save the EDX value to R8D register. And then I do a shift left, which is multiply the R8D by 4. And then subtract the R8D value by 4. And then plus the base address from RBX, well, EBX, okay, EBX, anyway. And then move the value that is currently in, I guess I have to flip this around, in memory location ART-AD into the register ART-AD. And finally, subtract the value of EAX with RAD, right? That's essentially implementing this instruction. The same functionality, but just different expression. And now I want you guys to discuss in group is that, so we have seen two different ways of expressing the same program. How does two expression implies or say, what do you think? What are the pros and cons for this two different implementation? Let me first try to send out the question from the chat, and then we can go into discussion. All right, seems like most of you are back. So what do you guys think? What's the good thing about the left-hand side? What's the bad thing about the right-hand side? if all your instructions are like the right-hand side, what's a good thing? What's a bad thing? Okay, so Vince.
With version B, if the instructions are enclosed to just these kinds of instructions, then the ISA would only need to define like a lesser set of instructions than version A.
Are you saying that if it's all like the right-hand side, then the ISA is only need to define a limited set of memory addressing mode?
Yes.
Okay. All right. What else? So Vince, you are in the Rocket 10. Okay. Who else? Elliot.
I think that maybe for version B, it would be easier to debug if something went wrong because you could separate it out into like which specific instruction like something was happening in versus it's all on one line in version A.
Okay, that's a good point. Easier to debug. Okay, what else? Okay, so maybe I can share you a few thoughts that I have, right? So S86 is designed pretty much like the version A, right? But the problem with the version A is that, you know, whoops, shoot. The problem with the version A is that you need your instruction becomes really complex, right? Like this sub L instruction itself has to do a lot of different things. Turns out that you cannot make your subtraction or say the LU really trivial or simple to implement, because suppose your subtraction instruction should only be taking two values and then subtract it, right? But now I have to look into, oh, now I have to figure out that where should I get one of my operands? And turns out if it's this complex, I have to figure out where in the hardware would help me calculate this before I can access, right? And then I have to access the memory location as well from before I can really use the LOU, right? So it's very, very complex. But on the other hand, right, for this pieces of instructions, the subtraction, no matter it's this one or this one, right, you always take two values, right? So the hardware is really, really simple to use, right? And the addition is also only taking two operands, right? And the shift only take two operands as well, right? And they are all in register or constant. So it's there is some kind of clarity in the instruction formats in this way. And only the move instruction has to deal with the memory. However, if we are smart enough, we are able to avoid this kind of syntax in the move instruction, then the move instruction can also be simplified in a way that it can also be in a format that we have the memory address available, or at least just at most just give you an offset, right? So this is make the instruction format a lot simpler to support. So decoding an instruction is a lot easier, and the number of instructions that the processor needs to support is probably not that a lot, because now, like if you consider this instruction itself as a separate instruction, then it can completely be eliminated by this set of other instructions, right? So if you use this philosophy, then a lot of instructions could be avoided when you are implementing the processor, or when you are designing the instruction set architecture. So turns out that this is the version B could be made hardware friendly. However, in terms of the programmer part, right, it takes more instructions to implement or execute the program, and need more register to make it effective. So that's also one drawback on the hardware side. So there is no perfect interface like what our debate earlier on the car, right? So like Tesla, they take the design that everything goes through the touchpad, but to use the touchpad, there is a learning curve, and sometimes the feature is hidden in a very far end from the user interface. However, if it's traditional car, just find a button and press it, it should be working, right? So that's a different design philosophy. So another design philosophy for the instruction set architecture is to simplify the instruction set design. So one of the extreme example compared against x86 is the one that we used in a textbook called MIPS instruction set architecture. So in MIPS instruction set architecture, all instructions are 32 bits, and it has 32-bit registers. So compare that against x86, right? So for x86, they only have this amount of registers. So in general, 16 registers. However, in MIPS instruction set architecture, we have 32-bit registers, and all registers are the same. However, if you compare with x86 instructions, x86 has a lot of limitation on what each is used for. For example, EX is used for accumulator, BX is used for base register, some of them is used for stack pointer, and this one is for instruction pointer. Some of the flags are used for conditional point codes, right? So not all of them can be used equally. However, that's not the case for MIPS instruction set architecture. And the other thing, right? As we mentioned, in x86, we have 900 plus instructions. However, in MIPS, there are only 50 different instructions. And this 50 different instructions still covers the basic arithmetic, load store, and branch and jump instruction. And like in the addressing mode of MIPS, there are, in x86, there are many, but in MIPS, there are only 3, right? So that's the whole thing of the instruction set architecture. So MIPS is actually the very first reduced instruction set computer, which we call RISC instruction set computer. So and the inventor of MIPS is indeed the author of the textbook. So that's why they use MIPS as the example in their book. And the MIPS is the only type of instruction, the load store instructions is the only type of instructions in MIPS to access the memory. So in MIPS instruction set architecture, their abstraction of computer is like this. You have a set of registers and they are all the same, equally long. And you have ALUs supporting this amount of instructions, and you have a program counter controls the execution of your program. And now, thinking about MIPS and x86, how many of the following statements are generally correct? like everyone has voted, and the answer is also divided. So why don't we go into group discussion to figure out what's the consensus? All right, let's wrap up in 5 seconds. 4, 3, 2, 1. Time is up. Okay, so interesting, huh? After discussion, I still don't see that you guys have some kind of consensus. So definitely a question that worth discussing among you guys. So can some of your group share your thoughts with us? Can some of the group share your thoughts with us? All right, so I have Elliot.
So we were thinking, it might be 2.
2. Okay, what are the 2?
So the first one, that x86 provides more instruction than MIPS. And
MIPS,
the
okay.
fifth one, an x86 instruction may be longer than a MIPS instruction.
Okay, how can you tell the fifth one? So I
So
kind of like mentioned the first one, right? How about the
yeah.
fifth one?
So we were seeing earlier that in an x86 instruction has like a lot of there's like a lot of ways in the instruction set, ways defined to like do offsets and things like that in a single instruction instead of separating them out into multiple instructions. So in MIPS, when you only have these 50 instructions, then you probably have to separate it out like that in order to do a similar operation.
Okay. 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 But how about others? Why don't you think the second one is correct?
Ingenious. We're not sure, but at least for like certain like simple, like yeah, certain simple instructions, we would imagine like the instructions are kind of one-to-one, like for like just like adding or something like that. You wouldn't necessarily need that many more instructions in MIPS. So I think to say that like usually you'd need more instructions using x86, we weren't sure about that.
Okay.
And then actually for the third one, we were just kind of unsure of like what it meant.
Okay.
And then the fourth and fifth one are at odds with each other, obviously. So yeah.
Okay. Hayat, any thoughts about it?
Yeah, I actually thought instead of 5, I thought it could be 4.
4. Okay. What are
Uh,
the
yeah, because I read in the textbook that
Mhm.
x86 has variable instruction length.
Mhm.
So that just I thought that if it has variable instruction length, then it might be shorter than a fixed length system.
Okay, it might be shorter. Okay, so this one,
Yeah,
what's the
and
other one?
I was unsure about I also thought it was 1
Mm-hmm.
4, and I was unsure about, so my group was unsure about 2.
2.
So yeah, but I
So
thought 1
how
and 4
many
are,
does your
it was between
so
2 and 3, B or C.
B or C? So you
Yeah.
guys, so which one you guys don't agree with? You don't agree with this one?
Uh, I mean, I don't know about the rest of the group, but I just remembered from the textbook that.
Okay. Other thoughts? Okay, so thanks for 2 of the group's insights. And I would say, so let me just show you another program that I just created earlier this morning. So to save the time, I hope you are convinced that I did created the program, and the program does reflect the code. So here's the code that I am compiling, and I'm actually compiling the sum function, which is the basically very similar to the example that I gave you. Is a for loop, but adding from two arrays instead of one array. And so if you look at the optimized version of the instruction, saying like the x86 version of it, right? The sum function, there are some beginning part of the code, and the main loop is actually here, right? So you can from the lab 2, you probably already have the concept of basic block. So the basic block here, and then they do move L, add L, move L, add L, move Q, add L, and J and E, right? And go back, right? And some interesting thing that you can potentially find is the format of the instruction could be really simple and very complex. Like this one, move L, right? It has 3 parameters for a single argument. But there are also instructions like move Q that only have 2 operands. There are also instructions like JNE only needs 1 operand, or instruction like the return doesn't have any other argument. So, and there are also instructions like push Q has 1 argument, and or instruction like jump has or CLTD, right? Has nothing, no arguments. So that's very different from the design of MIPS instruction set architecture. And also another instruction set architecture, which I just have, that is ARM, right? So for ARM, you can see that almost every instruction, well, the return instruction has 0 argument, right? But if you pay attention to the MIPS instruction set architecture, even they say no matter how long or how short the expression of the instruction is, it must be 4 bytes long. So, but for x86, an instruction may be only 1 byte, like the return instruction, like the pop instruction. They could be 1 byte or 2 byte. However, no matter it's a jump or return in MIPS instruction set architecture, everyone is 4 bytes long. And for ARM, it stays the same in a way that every instruction is also equally long. So it looks very contradiction, but both 4 or 5, they are correct that an x86 instruction may be longer. If you have a really complex subtraction instruction that would take 6 bytes to encode. And it may be as short as 1 byte. In that way, it will be shorter than a MIPS instruction. However, for MIPS, every one is 4 bytes long. Now, if you remember the table that I just showed you in the very beginning, right? An x86 instruction can access memory for 3 times, 2 times, right? For the data memory, right? Sorry. Oh, oops. An x86 instruction can access memory for 3 times. And the answer is still yes, right? So here we have a subtraction instruction. It would access the data memory for twice. However, because you have a 1 load, 1 store, right? But don't forget, in the very beginning, your instruction is also coming from memory. So you also need to access the memory to get the subtraction itself. So it turns out that an x86 instruction would definitely cause the computer to access memory for 3 times. So, and the second thing, that is the only thing that's not completely correct, because it typically, as we just observed, right, they have so many ways of expressing a program, or so many ways to compress the operation into a single instruction. So they potentially need fewer instructions to, most of the time, they need fewer instructions to express a program. So for the same loop, this is the ARM version. So if you count the number of instructions that the ARM version has in the loop, it's actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh boy. Okay. Keep going. Okay, let me see. So it actually take 24 minus 14, right? So 10 instructions, 11 instructions in total, right? But for the x86 version, it's just like 8 instructions in total for the loop, right? So it's typically shorter to express a program, given a single instruction can do a lot more than others, right? So this table gives you a very good comparison between MIPS and x86. MIPS instruction is fixed length instruction, so it's easy to decode. However, for x86, your instruction may be as short as 1 byte, as long as 17 bytes, right? So it's very difficult to decode. And the other thing is for the code size, which is actually talking about how many static instructions you have in a compiled program. And MIPS, typically you need more instruction, and for x86, it's typically smaller. Number of registers, MIPS are more, because you need more temporary value to be stored. Otherwise, this instruction set architecture won't work. And the addressing mode in MIPS is very complex, but it's very simple, but in x86, they support 4 different modes. So it turns out the hardware implementation on the MIPS side is simpler, but it's complex on the x86 side. So they represent 2 different types of instruction set architecture. So for the MIPS, that's actually the representative of reduced instruction set computers. And for x86 is the representative of CISC, complex instruction set computers. So if you look at the popular instruction set architecture that we have for now, like if you are having an Intel or AMD processor, you are on the side of x86. But if you are having an NVIDIA processor, if you are having an Apple processor for your mobile phone, for customized cores, typically it's based on instructions like MIPS or ARM. So and for among these instructions, except for x86, everyone else that is popular right now are RISC instruction set architecture. RISC type of instruction set architecture. And the main reason is just because this makes the hardware design a lot simpler. And if you have simpler hardware, it makes the clock rate, the production a lot easier than very complex hardware. So that's why we have such a distinction of instruction set architecture. And but don't forget, x86 has to look like this because it has its historical reason. And as many of you said, it's like Toyota or Honda in a certain way that we have to think about how our programmers use the computer in the past. So set architecture design is pretty aligned with the programming language. However, for RISC type of instruction set architecture, they are completely from the thought that how can we make the hardware simpler and make it faster? So totally different ways of thinking about things. So before you leave the classroom, there are several things I want to remind you. First, we have reading quiz due this Wednesday. The assignment 2 is already up on the website and great scope. You can start working on it. And we have some feedback from you guys, and many of you were talking about if we can explain the reading quiz. But I also found some of you feel the reading quiz is because, to be honest, a lot of the reading quiz questions are directly from the textbook sentences. So if you feel it's vague, it's probably the amount of time you spend in the textbook is you probably need to go through the textbook while you are doing a reading quiz. Maybe that's easier to help you. But if you still cannot get it, and if our quick and short answer on Piazza is not going to satisfy you, go to office hours. That's how we can help you learning. And some of you were asking about more examples. So first, lecture time is precious and limited. So I will try my best, but don't forget, we also have intensive amount of lab assignments, which give you those real examples. And the other thing is that a lot of you are thinking about operational problems, like how can I get this number right? But at the end of the day, you will figure out that the numbers are not that important. It's more about the concept. So that's why I would rather spend more time in a lecture talking about concept rather than how to solve a specific problems. Like differential equation. A lot of you learned in one of the engineering mathematical type classes, but I don't believe any a majority of you still remember how to use it. But the concept is more important, right? What point of time we need to use that. And some of you were asking about why not maximum scores. Well, so the thing is that why don't you try to get it right in very beginning, right? So these are my answers to that. Other than that, enjoy the rest of the day. I will see you in office hours tomorrow, or the TA could see you in the office hour. See you tomorrow.
I've cheated and I've lied, I've broke down and I've cried, I've got nothing to hide no more.